Yes, class. So in the last class, we had left at this question. No, this was a question from electric flux. So quickly, let us see the solution so that we can start with the last part of electric flux, that is application of Gauss theorem. So in the last class, we had seen Gauss theorem. What was Gauss theorem? Gauss theorem basically said that total electric flux that is present, is 1 by epsilon naught times the charge that is enclosed. So the charge 1 by epsilon naught times the charge that is enclosed by the closed surface. This is what is meant by Gauss theorem. And electric flux was what? Electric flux we had done earlier. That was the number of field lines that is passing through a unit area perpendicularly or making an angle of 90 degrees. So this is what it was, electric flux and Gauss theorem. Now, based on this, this was a question left. So this cube is not exactly placed on the center of the origin of the axis. This is at a certain separation A, and the side of the cube is also A. So separation from the origin is A, and the separation of the cube, no, side of the cube is also A. So we'll use the same formula. This is given to us, E is equal to alpha x to the power half, and we have to find the flux through the cube. Now see, when we are finding the flux through the cube, look at these surfaces. See, electric flux is along x-axis. So if you look at this part of the cube, area vector will also be here. So angle will be 0 degree, right? It means electric flux will exist because cos 0 degree is 1. So ES cos theta, somewhere we'll have the value. Similarly, look at this surface. If you look at this surface, this will be the area vector. So angle between the electric field and the area vector, this will be 180 degree. Cos 180 degrees minus 1, you will be having some value. But if you look around the rest of the surfaces that are left, look at this surface or the back surface or the bottom surface or this front surface. If you look, see, this will be n cap, this will go area vector n cap, this will be in front n cap, this will go at the back, that is n cap. All will be making angle of 90 degree with it, right? This will also make 90 degree, this will also make 90 degree. So cos 0 will be 90 degree. It means there will be no flux due to these four surfaces. So electric flux will only be due to this surface and this surface, E1 and E2. That's it. So now your work is easier. Otherwise, you'll have to calculate electric flux through every phase, through fourth phase, third, fourth, fifth, sixth, all the 6 phases. But now you can see all these 4 phases, since their areas vector are making angle 90 degree with electric field, ES cos 90 will be 0, so no flux. That's why I'm saying whenever you're solving questions of electric flux, the first thing that you should do is directly drop the area vector. When you drop the area vector, half of your work becomes easier because you have to check the angle between electric field and area vector. You do not have to take the angle between electric field and the plane of the surface. This I have been repeating a lot. We have seen also questions on this. Please be careful when you're solving. Now see, now this is our work. Let's say we are talking about this right surface. Let me write this as right. This is the left one. First, calculate is calculated for the right one. So this is given E is equal to alpha x to the power half. What is the surface area for this? We are just talking about this square, not the whole cube. We are solving it in segments. 4 segments were 0. 2 segments are left, right and left. So we are talking about the left one. So area, you see what we'll calculate? Flux will be, we have to also find out the charge. No, first let us find out flux. Flux through the right. It will be electric field through the right multiplied by surface area of the right. What is the surface area of the right part? A square only. And where is the area vector pointing? I cap. Remember on Monday also we had seen a question where XY plane was mentioned and 5 meter square was mentioned. So no I cap, J cap Cartesian form was mentioned. No unit vector was mentioned. So how did we analyze? Where the unit vector went, that is perpendicular one we had chosen, remember? So here also A square is the area, but what is the unit vector that you'll put along with the surface area? You'll put I cap. Why you will put I cap? Because the area vector is pointing towards the I cap. That is your x-axis, fine? Now, electric field is what? Electric field is already given, alpha x to the power half I cap. Electric field is already given in the question that this is along I cap. Now, what will you put as x? X is the total separation from the origin. So for this square that is present on the right side, separation from the origin. Can anyone tell me what is the separation from the origin for this right cube, right square? This one. 2a. Very good, Austin. This is 2a because a from the separation of the cube, from the origin of the axis to the cube plus this entire length. So entire separation becomes 2a. So we'll put E is equal to, this will be alpha will remain. Instead of this, we'll put 2a to the power half, or you can write root 2a I cap. Right? This is it that we require. Now put in the formula. Flux will be electric field, that is alpha root 2. You can do one thing, shift a aside, keep a as half only, because we have to solve this a also, no? So if you put it under the bracket, it would be a little difficult to solve. Keep a like this only, right? You can write no alpha root 2 separately and root a, that is a to the power half separately. That's what happened. So that just this a is free, dot, because I cap dot I cap will be 1. So this I cap dot, and what is the surface area? A square I cap, right? So I cap dot I cap will be 1, that we already know. So what is left? Alpha is left, root 2 is left. Now half plus 2. You're having, this is going to be 4. This you will subtract this. So this will be 3 by 2. So a to the power 3 by 2, right? And I cap got cancelled. This is flux towards the right. Now flux we'll calculate. This is right only. So one side is left, that is the left side. What is the change that is going to come? See, side will also remain same, but for surface area, area vector is pointing towards the left side, that is negative x-axis. So surface area will be minus I cap. All right, electric field will be I cap, but surface area will be minus I cap. A square minus I cap. Why in the first one we wrote I plus I cap? Because it was pointing towards the right. Now it is pointing towards the left. This is how you drop a perpendicular to the surface. So for the flux for the left one, you will do the same thing. EL dot surface area for left. But the surface, this surface area for left, you will write this as a square minus I cap. Right. And what is the difference in electric field that will arise? See, alpha x to the power half I cap, x won't be 2a. X won't be 2a. This is the square. Separation from the origin is just a. Separation from the origin is just a. So E L is going to be alpha. This is a to the power half I. So this is electric field for the left. Now calculate the flux. Put in the values. Electric field for the left, alpha a to the power half I cap dot a square minus this. So this is going to be, again we are subtracting this. So this becomes okay, same thing, minus alpha a to the power 3 by 2. Because of the just minus sign. Because we are multiplying this term. So same answer we are getting, it's just that here we are having minus I cap. So one minus sign is there. Now what is the net flux that we have to find out? See, net flux will be flux because of right plus flux because of left face plus flux because of top face plus flux because of bottom face plus flux due to front face plus flux due to back face. All the 6 faces of a cube. But see, out of which right is root 2 a to the power 3 by 2, alpha root 2 a to the power 3 by 2. Left is minus alpha a to the power 3 by 2 plus rest of these top bottom, they are 0 because theta was 90 degree for all of this. Initially only we had clarified this. So now flux will be root 2, you can write 1.4. So if you subtract 1, you will get 0.4 alpha a to the power 3 pi. This is your net flux. And in the question, charge was also asked. See, if you have flux with you, what you can do? Through Gauss theorem, you know flux is equal to charge enclosed divided by epsilon naught. Flux, you have calculated it from here. Epsilon naught's value, you already remember 8.85 into 10 to the power minus 12. Can you not find out the value of charge? Charge will be simply flux, that is 0.4 a to the power 3 by 2 alpha multiplied by epsilon naught. This much will be the value of charge. Yeah, so it's a lengthy question, and I think in your assessment also this type of question was asked, but because of lack of time we couldn't complete it. It's a lengthy question, but this will summarize all of the concept that is required so that we can now shift on to some other topic. Note it down quickly, all those who haven't. The question part, I think some of you have written, no, and solution all of you write. Then we'll do some.
Can you scroll up?
This is the starting only, the question. This is just the graph plotting is there. Atia Sultana, who is this?
Man, this is me, ma'am. I'm joining from laptop now. You leave like.
Okay, okay.
But
R is right. It's just to differentiate between the faces. This is the right face. This is the left face. Both, all the rest of the four faces are zero. Flux is zero because they are making angle of 90 degree. That's why this is the right face, left face. So that's why I've written ER and SR. SR means surface area of right. We write no formula of flux as ES cos theta. So E for right, surface area right, this way. Now, look, this is just the last part of the lesson. That is Gauss theorem we have done, applications of Gauss theorem. But see class, for understanding the application of Gauss theorem, for understanding the derivation of applications of Gauss theorem for line charge, for plane sheet, for spheres, you have to have the knowledge of continuous charge distribution. Continuous charge distribution is a very easy topic. We'll discuss it in detail right now so that we can understand the derivations of applications much easier. See, three types of continuous charge distributions are present. One is when charge is distributed on a linear surface, on a line, that is linear charge distribution. This is the first one. If charge is distributed on some area, let's say this is some area, charge is distributed on some area, so that we say is superficial charge distribution. If charge is distributed on certain volume, let's say a sphere is there, charge is distributed over it, so volume or cubical charge distribution. That is what is meant by linear charge density and charge distribution. So linear charge density means you have a straight line. Even if you do not, whatever is the charge that is distributed per unit length, we call it as linear charge density. We represent it through the symbol lambda. So what will be the formula? Q is the total charge, L is the total length. So charge per unit length, this is it. Because we'll be requiring it, that's why we are studying it. You have most of the formula in terms of lambda, so you'll not be understanding lambda. That's why we are discussing this separately. So lambda is Q by L. So this is for uniform. Suppose if this is non-uniformly given, this is non-uniformly distributed, so in that case what you will do? In that case you will simply differentiate charge per unit length. This is in case of non-uniform. And class, just understand the first one, rest of them are based exactly on this pattern. Others, the rest of the charge distributions are based exactly on this. And what will be the SI unit for this? See, charge is coulomb, length is meter. So charge, for example, if I give you this pen, charge is distributed over this surface. If I want to find out what is the amount of charge that is contained in just 1 meter or in this unit meter, so what will I do? Charge per unit length. Fine. So that is what is meant by lambda. That is linear charge density, charge per unit length. So how to apply both these formula? Let's see. I'll give you two situations where one will be uniform. So you will understand how to apply lambda is equal to Q by L and when to apply lambda is equal to dQ over dL. See, this question says that charge of 10 coulomb is uniformly distributed on a wire of length 5 meters. You have to find out linear charge density. So linear charge density for the first part, lambda will be charge per unit length. What is charge? 10 coulomb. What is the total length? 5 meters. So that means 2 coulomb per meter. Second part is asking what is the charge on 2 meter length of wire. This is very baby-like question. See, in unitary method we used to do in schools in the lower classes, where if 10 coulomb is for 5 meters, how much charge will be for 2 coulomb for 2 meters? Simple unitary method you can apply. Directly also many people will do 2 centimeter. If 1 meter has, this is like, what is meant by this? 2 coulombs per meter. This means in 1 meter, you are having 2 coulomb of charge. So in 2 meters, how much charge will you have? 1 meter is having 2 coulomb. So 2 meters will have how much? 4, right? This will be 4 coulomb. Exactly. This will be 4 coulombs. So lambda, this will become 4 coulomb per meter. This is a lambda for the first one. Now, one thing I wanted to tell you for differentiation, that also have a look. See, if the question is given to you in this form, linear charge density of wire lambda is 2x. Now calculate charge on 10 meter length of wire. This is non-uniform, right? Because your length is not fixed. If you will put x as 1, lambda will be 2. If you put x as 2, lambda will be 4. X as 3, lambda will be 6. So your lambda has variation And when there is variation, uniformity gets disturbed. Then we land into non-uniformity. So linear charge density of wire lambda is equal to 2x. So lambda is given as 2x. What I have told you, lambda is equal to dq over dx. I think x is written, so it's better we prefer x. This is length only. But we have to find out charge in this case. Had charge been given, we would have differentiated and we would have got lambda. But in this case, charge is only missing. So we'll integrate it. Differentiation and integration, they are inverse operations, no? So if we had to solve it through differentiation, other term we'll get it through integration. So what will be dq? dq will be equal to lambda dx integration. So the entire integral of dq will give you the complete charge that we are supposed to calculate. Lambda is given as 2x dx integral. Now see, 2 is common, take it out. How will we differentiate x? The formula for the differentiation is x to the power 1. What do? Add 1 in the numerator, in the power, and whatever is obtained divided in the denominator. So x will become x square by 2, right? And limits are also given 10 meters. So 0 to 10 meters. 2 gets cancelled. Charges. This is how you will use it in both the cases. Linear charge distribution for uniform we had seen, where charge was fixed, length was fixed. Now, if length is non-uniform, what will you do? You will perform it like this. Suppose, let's say in this question, lambda was given. Suppose in this question, charge was given, lambda was asked. So you would have differentiated dq over dx and you would have got lambda. Since in this question, lambda is only missing, that's why we are calculating. Since in this question, only charge is missing, that's why we are integrating it and calculating it. This is simple integration from here. X to the power 1, how do you differentiate? Take 2 common. Yes, any doubts?
Can you just explain once again? Your voice is lagging, so I couldn't.
Okay. This question, this part?
No, from starting, your voice is lagging, so I couldn't listen.
Okay. See, just rest of you also revise. Linear charge density means charge per unit length. Fine. So lambda we represent linear charge density as lambda. So lambda will be charge per unit length, that is Q by L. Now, if your length is uniform, you will use lambda is equal to Q by L directly. How? Look in this question, we have seen. Charge was given 10 coulombs, length was given 5 meters, 10 divided by 5, 2 coulomb per meter, lambda is obtained. This is uniform, right? Now, if we have non-uniform section, suppose this, where lambda is given as 2x.
Why only this part and this?
This is non-uniform. So what we'll do? Lambda is non-uniform, so we'll differentiate it, dq over dx. But in this is the formula. You don't differentiate. This is basically the formula for non-uniform. Now, this is given, dq is missing. So what we'll do? We'll integrate it. This will go here. We'll integrate it, and this is how you perform integration. Put the value of lambda as 2x because this is provided in the question. Integrate it from 0 to 10 because we have to find up till 10 meters. So x to the power 1 will become x square by 2. This is how you integrate. If anyone is having difficulty in integration, then let me know personally. Otherwise, I think 2x integration of 2x, everyone would be able to solve it. So now what will happen? 10 square minus 0 square is 100 coulombs. Linear charge distribution is clear to all of you now?
Yes.
So note it down, note the entire part. We'll then go to the superficial charge distribution. Make the heading as continuous charge distribution because without this, you won't be able to understand rest of the physics better. Though, if even in one line we could have completed it that lambda is Q by L, but let us study it in detail. Integration part. See, just remember when you are integrating, no, x to the power n is there. If you are integrating it, x to the power n was there, add 1, whatever is given. And now whatever is the power, divide it here, n plus 1. So suppose x is given, no power is there, it means power is 1. So this becomes 1 plus 1 and it gets divided by 1 plus 1. Suppose x to the power 2 is there, add 1, what is left? 2 plus 1, 2 plus 1. X to the power 3 is given, add 1, divide the entire term by the power that is created, 3 plus 1. So that's how we write this as x to the power 3 by 3, x to the power 4 by 4. This became x square by. Now clear? Now see, the next one is superficial charge distribution. So superficial charge distribution means same thing, charge, but per unit area. Everything now, once you have understood the first one, second and third ones are very easier, very easy. See, this was first one, linear charge distribution was charge per unit length. If we have charge per unit area, then we'll say superficial charge distribution, or aerial charge distribution is also said, but we use the term mostly superficial charge distribution is used. So S is the surface area of a surface, Q is the total charge. So surface charge density is charge per unit area. We represent it through sigma. Lambda was for linear, this is for superficial. So charge per unit surface area. Same thing, this you will use for uniform. Now you'll be able to manage. And yes, what about the SI unit? Charge is coulomb and area is meter square. There it was coulomb per meter. Now it is coulomb per meter square. And again, same thing. If this is non-uniform, you will use dq over ds. Now, one question, let us see one easy question so that we are familiar with the formula. This says that a charge of 10 coulomb is uniformly distributed on the surface of a sphere of radius 2 meter. Calculate surface charge density, calculate charge on 2 meter square area. See, sigma is charge per unit surface area. What is the charge given? Charge is 10 coulomb. What is surface area of a sphere? Surface area of a sphere is 4 pi r square. So this becomes 4 pi into r. Radius is 2. So 2 square. So 4, 16 pi meter square. So what will be sigma? Sigma will be 10 divided by 16 pi, or we can cancel and write it as 5 by 8 pi coulomb per meter square. This is sigma. Second part says, see, now again coming back to the definitions, this means what? In 1 meter square, there are presence of 5 by 8 pi coulomb of charge. So in 2 meters, you will have 2 meter square will have 5 by 8 pi into 2. That is 10 by 8 pi, or you can write this as 5 by 4 pi coulomb per meter square. Right, so 1 meter square has this much charge. So 2 meter square will have this much. This is how you write it. Similar to what you have studied in the first one. Quickly note it so that we can start with the last one. Q by epsilon naught, that is the formula for electric flux. Tarif, that is the formula for electric flux. That is right what you are writing. We are discussing charge which is distributed over a surface area. That will be Q by surface area. For the way it would be for linear, it was charge per unit length, charge per unit area. Next, we'll see charge per unit volume. Q by epsilon naught is right, but that is the formula for flux. And we represent that through phi. This is sigma. Linear was lambda. Clear? Last one is charge per unit volume. So if cube, this is in 3D, like if you have a cube, if you have a cuboid, a sphere, a cone, so charge can be distributed within the surface also. No, if a sphere is there, charge is distributed only on the outer part. That means it is distributed on the area. But if charge is distributed within, then we can say this is charge. Charge is distributed inside the
Ma'am, can you
volume.
just scroll up?
Yes,
Uh,
Chavez?
can you just scroll up for a second?
Yes. All right. So if suppose charge is distributed at a inside the volume, so we'll not at that time we'll not consider the charge that is distributed over the area. So for a sphere, if the charge is distributed over the surface of it, we say that this is charge is distributed per unit area. But if it is within, present inside it, so we say this is charge per unit volume, right? Written?
Yes.
So here we'll use charge per unit volume. Now see, lambda was for that symbol. Lambda was for linear charge distribution. This symbol sigma was for superficial charge distribution. We use the symbol rho, that is charge per unit volume. So this becomes Q by V. Again, the same repetition. This is for uniform. And what will we write the SI unit? SI unit will become coulomb per meter cube. Coulomb per meter square, coulomb per meter cube. And again, same thing, if this is non-uniform, dq over dv. Right, this is for non-uniform. One last question based on charge distribution. Let us see. A charge of 10 coulomb is uniformly distributed throughout the volume of a sphere of radius 3 meter. Volume charge density. See, volume charge density is rho, is charge per unit volume, right? Charge, what is charge given? Charge is 10 coulombs. Volume of a sphere is 4 by 3 pi r cube. So 4 by 3 pi. Radius, what is the radius? 3 meters. So that this becomes 3 into 3 into 3. 133 gets cancelled. 9, 4, 36. So this becomes 36 pi meter cube. So rho will become equal to 10, that is charge, divided by volume, 36 pi. So you can reduce this and you can divide it by 2. So this becomes 5 by 18. 5 by 18 pi coulomb per meter cube. This is rho. So this says that charge on 3 meter cube of volume. So see, for 1 meter cube had 5 by 18 pi coulomb. So how much is asked? For 3 meter cube, this will be 5 by 18 pi multiplied by 3. So this gets cancelled, 3, and here we get 6. So 5 by 6 pi coulomb per meter. Coulombs, we are calculating the charge. No, this will be coulomb. Fine, same thing, just one more addition of dimension, that is volume. This is the last one, volume charge distribution. Note it down.
I mean, area also you wrote coulomb per meter square.
Yeah, this is because we are calculating the charge, no? So this is coulomb per meter. This is charge, we are calculating the charge. Second part of the question is asking us to calculate the charge. Distribution is in the first. D is when we write differentiation. See, you must have used in differentiation. Like if we write velocity, velocity is dx over dt. This is differentiation. See, now for the applications of Gauss theorem, we'll be using Gaussian surface. So I have mentioned you earlier also that we draw a Gaussian surface for the calculation. So just remember two conditions that for Gaussian surface should be closed and electric field should either be perpendicular or parallel to the Gaussian surface. This is just a condition for Gaussian surface. So if suppose you have a wire, straight wire, charge is distributed over the wire. Preferable Gaussian surfaces, draw a cylinder. That's it. If you are having a sphere, charge is distributed over the sphere. preferable Gaussian surfaces, draw a sphere, choose a sphere. So we'll be using this line linear charge one right now. Hmm. So electric field due to infinitely long wire. So what we'll do, infinitely long wire was there. We wrapped it inside the Gaussian surface, that is the cylinder. We are just calculating electric field for the wire, but we are taking the Gaussian surface as this cylinder. So now how many faces are there? See, electric field, this is going past the electric, it is perpendicular to the wire. Now see, if this is perpendicular to it, this is our condition. Again, I'm telling you, you are not calculating electric field for the entire cylinder. You are calculating it for a wire. If you have, suppose I give you this wire, this is a wire, and I'm asking you calculate the electric field for this particular wire. What will you do? That is the derivation which you have to study at the last. Just remember the formula for it. See, there will be three surfaces here. One will be this curved surface, this curved surface. So 1, 2, and this is the flat circular surface, second flat circular surface, and one curved surface. This is how now we draw a cylinder. See, if you have a cylinder, this is how now you take the cylinder. So this part becomes, this is the curved surface area. The above, top, and bottom are the flat circular ones. So this is what is this is what is required by us. So if you take the area vector n cap here, upwards and downwards, this would get vanished because theta is 90 degrees. So phi 1 will be es cos 90 degree 0. Phi 2 will be es cos 90 degree 0. Wherever you're not understanding, please stop me, because this is a derivation. Once derivation is done, only formulas are discussed. All right. Now, third surface. Third surface, we require the third surface. So for the third surface, we'll use ES, right? Surface area for the circular part, curved surface area. Remember, if you are having a cylinder, what is the surface area for it? 2 pi RL. For a circle, we write 2 pi R. If length is added, that is cylinder. Yes.
Ma'am, here why we cannot calculate the direct value of wire without taking the cylinder?
This is infinitely long. The problem is this is not a finite wire that you can calculate. So for infinitely long wire, how much length will you calculate? That's why we have just taken a segment of it and we have wrapped it inside the Gaussian surface so that we can apply Gauss law. Fine?
Okay.
Now see, surface area will be 2 pi RL. If L is the length of the wire, so surface area will be 2 pi RL, where L is the length of the wire. Now, flux was what? You were mentioning, no, that if you were even asking what is Q by epsilon naught, why it is not used. So see, this is getting used here. Since Gaussian surface is there, now we are applicable to use the Gauss law. So this becomes Q by epsilon naught. This becomes equal to Q by epsilon naught. Now, what you can do, you can put the value of Q. So see, if a wire is used, out of all the charge distribution, which you should prefer, if a wire is used, linear, superficial, or volume? If a straight wire is used, linear. Good, linear. Yes, Austin and Chavez, this would be linear. So what was linear charge distribution? Linear charge distribution was lambda was Q by L. So what will be Q? Q will be equal to lambda into L. Put it here. Flux becomes equal to lambda L by epsilon naught, right? Just putting the value of here flux. So now you have this flux here. one flux is there. Can we equate both these equations? This is first equation where flux is equal to E is equal to 2 pi RL. We have second flux. This is equal to Q by, not this one, which we have just now written. Both are equal. So what you can do, you can equate this 2 pi RL, E 2 pi RL equal to lambda L by epsilon naught. Length gets cancelled. E becomes equal to lambda by 2 pi R epsilon naught. This is the formula for electric field for a linear wire. If a linear, see, we calculated electric field for point charge. Remember, E is equal to KQ by R square. That is for point charge. That is for a sphere. If a linear charge, if a wire is mentioned to you, a long straight wire is mentioned, then directly use this formula. You know now what is lambda. Lambda is linear charge distribution. R is the radius of the cylinder. Epsilon naught is the permittivity of it. E is the electric field. So electric field is inversely proportional to the radius of the cylinder. This is how the proportionality graph will be equal to. E is inversely proportional to the radius. Please note it down quickly.
Yes, cool. Yes.
Last topic for today. Rest of the questions we'll practice in the next class. If a infinitely plane sheet is given. So for infinitely plane sheet, we have just taken a portion of it as we were doing it for the infinitely long wire. Now we'll not use lambda, we'll use sigma because charge is now distributed on the area of it. So the Gaussian surface that is preferred in this case, this is a cylinder. A cylinder is preferred which pierces through the infinite sheet. All right. Now, see, again, we will have the curved surface area. See, electric field is in this direction. This is the electric field, which is perpendicular because we are choosing electric field that has to be perpendicular or parallel to the Gaussian surface. So this is see, for this surface n cap, this time this n cap, this area, this flat circular area, this is parallel to electric field. So this time it won't be 0. Or if you choose this won't also be 0. If you take this first part, this is the second part, this is the third part. Now first and third part, they are not 0. You will be having flux because of first part and third part. But now see, if you take this curved surface area, for the curved surface area, this is perpendicular to it. So n cap will be perpendicular. So this time, because of this curved surface area, you won't be having any flux, right? So flux will be only due to phi 1 plus phi 3. That is both the flat circular ends, not the curved surface area. So this is electric field into the surface area plus electric field into surface area. That is 2 times the electric field into the surface area. This is 2Es. Now flux will again be Q by epsilon naught using Gauss law. This is using Gauss theorem. So now charge, you will not use charge is distributed over the surface. So you will use superficial. This time we'll have sigma as Q by A, or Q, you can write it. This you can write the surface area. I'm writing it as S. No, so let me write this as S. So this is charge per unit surface area. So charge will be equal to sigma into S. So flux will become equal to sigma S by epsilon naught. Now this is one of the flux. This is the first flux. This is the second flux. You can equate both of these. So see, 2Es is equal to sigma S by epsilon. SS gets cancelled. Electric field becomes sigma by 2 epsilon. Graph C, now this is independent of radius. Do you see any radius within this question? There isn't any, there isn't presence of any radius. So whatever is the radius of the cylindrical Gaussian surface that you have chosen, electric field will be independent of. The rest of the formula part, some more things are left. One more class is needed to finish off this lesson. That we'll complete this lesson on Monday now. So quickly note down this infinitely plane sheet part as well. Just text me done once written. What about others apart from Austin and Tarif and Humam? Shave is done.